Now back to some thing again outside the scope of this class, some formal mathematics. Um, I pointed out that random variables have probability distributions. We've already seen in the last lecture two types of distributions, Gaussian distributions, or the so-called normal distribution, and uniform distributions. For looking at events where two types of distributions are particularly important, Poisson distributions are binomial distributions, although due to the law of large numbers, they actually tend to look Gaussian when you apply them many times. The binomial distribution is what you get when you toss coins. If you toss coins 500 times and ask how many times you get heads, the number of times you get heads will be governed by the binomial distribution. Poisson distribution is sort of the continuous version of that. You have a nuclear bunch of nuclear matter, and you count the number of decays per time, and there's a uniform probability lambda dt that um, a nucleus decays in time dt. And you can actually use either because they are essentially the same for in the limit we're working. Um, but I want to point out, we do need to make one assumption, and that's made and sort of implicitly throughout all this analysis, that every event is independent of the previous events. When those two protons decide to collide, they don't remember what the previous protons did. They just do their thing independently of all previous events. So that's what's called an independent random variable. The other concept that's pretty important is identically distributed. I told you that the theory of proton-proton collisions gave you probabilities of things happening, so it gives a probability distribution. Every PP collision has the same probability distribution. The chance of getting a Higgs is the same chance every time. And most data analysis problems you will come across have this feature of independent, identically distributed random variables. And this really task of mathematics here, it gives us the most important result, and that is that if you look at the mean and compare it to the error divided by the mean, if we take n observations and calculate, say, something gotten by taking all n together, which is possibly by summing them up, or taking their mean or something like that, the error over the mean is 1 over the square root of n. And that's written out here in the so-called law of large numbers, but we don't need to go into those details. It defines what the mean we can think of as the average value. That's the expected value of that random variable. And the standard deviation is effectively the error, and we don't have to worry about it, just have an intuitive idea what error is mathematically defined here, the square root of the average value of x minus mu squared, but we don't care about that. And then what counts is this. Error over mean is 1 over square root of n. So if we take n events, 1 over the square root of n is square root of n. So if I observe n events, my error is square root of n. Very important result. It has lots of impact on the amount of effort needed to do something. Namely, if I want to reduce the error by a factor of 2, which is a reasonable goal, I actually have to take 4 times the time. Because if I only doubled the time, I would reduce the error by the relative error, which is all that counts, by the square root of 2, whereas I wanted 2, so I need 4 times the time. So this is, I say, here we're looking at the theory of events and counting data, and this covers all sorts of things, in particular surveys. If you have n responses to a question, that's equivalent or similar to counting n events in a histogram, and the error is square root of n. So that's why you'd like lots of people in your survey, because otherwise you will get a significant error. And we will try to quantify these things in a little Python piece of code where let's do a slightly artificial case, try to get pretty pictures, where we have a lot of where we actually count the same number many times. We'll do that by imagining a situation where we have a survey which has 40,000 possible answers. We'll actually change this number later on, but here we're going to initially do 40,000. And let's suppose we had this survey with 40,000 answers, 40,000 questions, and assume each question was equally likely. And we did 1 million people in the survey, then the expected number of events in answers for each question is 25. And the error in 25 is 5, square root of 25. So what we're going to just plot then is we'll just look at all possible answers, 40,000 of them, and just plot the number of times that question was answered positively. So this gives you a histogram, and that's shown here for 25 events counted for 40,000 times. Here is 25. This thing is so-called 1 sigma array, so it's 30. And this is 1 sigma away the other side, that's 20. And I like to stress that you have 2 types of square root of n here. We have square root of 5 this way, and we have around the square root of 3,000 here, because there are around 3,000 answers for 3,000 counters of the 40,000 got are in this bin and on this bin, and the square root of 3,000 is whatever it is somewhere around between 50 and 60. So we have 2 square roots. We have a square root for the number of events in each bin, and we have a square root for the width of this distribution. This graph here points out that if we go to the above 30, this region here is 30 up here. Then actually this red curve here, which I didn't actually discuss on the previous slide, is the so-called normal distribution. And we, as I stated, most things in life have normal distributions. This particular case, because 25 is not a very big number, doesn't exactly agree with a normal distribution, but it's pretty close. Look at this graph here. It's the red and the green curves are pretty close. However, you will find that below 20, the green curve systematically lies below the red curve, and above 20, it lies above. And that's shown here. We have the real estimate of the errors, and you can see the green curve is above the red curve by amount much greater than the errors. So there is a systematic shift here, which is just not important, because you tend not to look at things in this detail. You don't usually take 1 million people in your survey and get such good statistics. So as I said, we would get this if we asked 1 million people a question with 40,000 answers, or if we took 1 million physics events, each with 40,000 outcomes, each equally likely. So either of those cases is governed by this simple case. Here's what I pointed out, that if you look at the middle of the distribution, 24 to 25 and 25 to 26, the red curve expects 3176 events in each of those bins. We observe 3179 and 3132 from our Python code, which is certainly within the square root of 3176, which is 56. So near the middle of the curve, which is really what counts, because that's where most of the data is, we get good agreement between the normal distribution and my Python experiment.